So hey guys, again we are going to start with the Leetcode daily challenge, and let's see what we have today. So let's go for it. And okay, oh, yeah, okay. So fine. Today we have a hard question after a lot of days. Okay, fine. So let's start with it. So it's a graph question. Okay. So there is an undirected weighted graph with n vertices labeled from 0 to n minus 1. So okay, n nodes are there, 0 to n minus 1. You are given the integer n and an array edges where edges has three elements. Edges I has three elements. U, V and W means the starting vertex, ending vertex and the weight of it. And it is undirected weighted graph. So we are gonna make a adjacency list because it's undirected. So 0 to 1, 1 to 0 will have same weight. A walk on the graph is a sequence of vertices and edges, and the walk starts and ends with the vertex, and each edge connects the vertex that comes before it. Okay, and the vertex that comes after it. It's important to note that walk may visit the same edge or vertex more than once. You find we are just walking around, and a walk can have same path again and again. That's fine. The cost of walk starting at node U and ending at node V is defined as the bitwise end of the weights of the edges traversed during the walk. In other words, if the sequence of the weights encountered during the walk is this, then the cost will be calculated this, and end denotes the bitwise end operator. So we are given a query, 2D array query, where a query is S and T. S is the minimum, and for each query we need to find the minimum cost of the walk starting at index S and ending at starting at vertex S and ending at vertex T. If there exists no path, no such walk, we can return -1. Fine. So in this example, it's like 0 to 1 is the edge whose weight is 7. 1 to 3 is edge whose weight is also 7, and 1 to 2 is an edge whose weight is 1. Okay. So it's like this one. N is given 5. So 0, 1, 2, 3, 4. 4 vertex are there, but yeah, we can see that 4 is isolated. 0 to 1 is edge, 1 to 2 is edge, and 1 to 3 is an edge. And vice versa because it's an undirected graph. So in the first query, we need to find the cost of the walk from 0 to 3, minimum cost. Okay, 0 to 3, can we go? Yeah, we can go because they're in the same component. 4 is a different component, so if we are given 3 to 4, we cannot go from 3 to 4, so it will be -1. Okay, let's start with the basics first. Let's form a adjacency list and see what we can do here later. So we are gonna have a 2D 2D array or vector, which will be basically our adjacency list, and it will be pair of pair of for every vertex. For every vertex we'll have a pair. We have a weight also, so we need to uh, we need to consider that also. So let's form a pair here, int and that's an adjacency list of length n because n vertices are there. So we will traverse those edges, like for auto e of this edges. For auto e of these edges, we will do what is that adjacency of e0 starting point will push back a pair which will be e of 1 and e of 2, right? In the pair, the first element is the ending index and the second element is the weight of it. And it's an undirected graph, so we are going to do 1 to 0 also with the same weight e2. Fine. This is our adjacency list. See, now here we need to find the weight or minimum weight of the walk. Okay. One thing we can see for sure is that we can walk only inside only one component. Okay, we cannot travel from one component to the other component, right? So one thing is clear that if we encounter a query where the starting and ending index are belonging to different components, then it will be a -1, right? And for rest of the queries where both the vertices ending and starting belongs to the same component, that will have an answer. And what will be that answer? Now that is to be minimum. And the answer will be consisting of the bitwise and of all the weights we are traversing. So one thing we know about bitwise and, see, there are some things about bitwise and that we know about. If A and B are there, so A and B, first thing is it's commutative, associative, sorry. So A and B is will be equal to B and A. We know that for sure, right? Another point is that, yeah, and operator, wherever and operator is applied, it will decrease the result. Means A and B will always be less or equal to the minimum of A and B. So see, and we are given that we can traverse the same path again. So if we consider this one, 0 to 3, we have two ways of going there. 0 to 1, 1 to 3. In that case, the weight will be 7 and 7, and A and A results in A only. So it will be 7. The answer will be 7, but we have to find if there is anything minimum than that. So it will be 7, 0 to 1, 1 to 2, 2 to 1, and then 1 to 3. That is also one path. So 7 and 1 and 1 and 7. So basically 7 and 7 will result into 7 and 1 will result into 1. And then we have to find the result for 1 and 7. That will be our final answer and that will result in 1 and 7. So 1 and 7 will result in 1. That's why the answer is 1 here, because we have taken this path 0 to 1, 1 to 2, 2 to 1 and 1 to 3. That will give us the answer. That is minimum. That is less than the other path which is 0 to 1 and 1 to 3. So one thing is clear, that the result will decrease every time we add up edge in our walk, right? So within a component, if we have a query which has the vertices both belonging to the same component, then one thing is clear, that the answer will be minimum if we add as more edges as possible in the walk, right? And how many maximum edges can we add to the walk? It will be like covering all the edges. Yeah, covering all the edges which are there in that component, right? If we get any two vertices in this component, like it was 0 to 3, but let's say it was 0 to 2 also, then what will be our answer? Minimum answer will be same for any two component we pick out of this component. Answer will be same for 0 and 1, answer will be same for 0 and 3, answer will be same for 0 and 2. Now you will say, how will the answer be same, that is 1 for 0 to 1? Because 0 to 1, the answer is 7. Okay, but that's just one way of doing it. Another way can be 0 to 1, 1 to 3, 3 to 1. Means the end vertex should be 1 no matter what path we take and how many times we traverse it. And other path we can take 0 to 1, 1 to 2, 2 to 7, 2 to 1. That will give us the result 7 and 1 and 1, and that will also be the answer will be 1. So yeah, now the question sums up to what is that every component will have same answer. If the query has the vertices which are belonging to the same component, then the answer will be same for all the cases. And if the vertices are belonging to different components, then the answer will be -1. Now we have two things to do. First thing is identifying if the vertices are belonging to the same component. First thing. Second thing, identifying the answer for each component. The answer for each component is and of all the weights in that component, right? 7 and 1 and 7 is what? 1. Now 1 will be the answer for any two vertices of this component, right? And 3 to 4 it will be -1. So now how to do that thing that we identify that if the vertices are from the same component or not. So for that purpose, what we can do here is that, okay, so what we can do here is, okay, let's make identification for each component. That let's make an identification. Okay, so and another thing is we need to find the minimum weight for each component. Fine. So what we can do here is that okay, so let's make firstly integer vector which will be components. Its size will be n. So every index, at every index we have, like at index 0 we have vertex 0. That will tell us that 0 vertex belongs to which component. And if the components 0 is equal to components 4, which means that they belongs to same component. Okay, that will be basically meaning that they are belonging to same component, they have the same value at their indexes in this vector. Okay, so initializing the identification with 0. Okay, the component 0 will be equal to 0 initially, and yeah, correct. And also while finding the answer for that component, while finding the minimum weight for that component, we will be traversing all the neighbors, means through BFS or DFS, any of it will work. We will find the cost with BFS or DFS, any of the method. Okay, and while doing that we will obviously, like for 0 we will be traversing its neighbors, and while traversing its neighbors we will set their value as that same ID. So we don't have to do the same process for 1 again, because 1 is already visited and we know that it belongs to the same components as 0, because while traversing 0 1 was there. While traversing 0 4 won't be there because it's in the different component, so 4 will have a different ID than 0. So we can take a visited vector, so that we know that we have visited this vector. The identification has already been done for this. We don't have to go there again, and answer will be same as 0. So it's basically visited and it's n and 0, that initially all are unvisited. One means visited. So we will go to each node. We will go to each node, I less than n, I plus plus, n nodes are there. We'll go to each node and we will see what is that if that node is not visited, if that node is not visited. And also let's make a vector which will be int and which will be cost of each component. Okay, cost of each component. Okay, fine. So component cost dot push back. Okay, in the cost vector we will push back what, let's say we will find the cost with this function. It will take input as the initial node, starting node, the adjacency list, the visited vector, the component vector, because we will be setting the same ID for the component, all the elements of that component. Okay, and then we have the id here. Let's now go with this function that will return an int value, obviously. So int solve, and that will take int starting point. Okay, it's a node basically, vector pair that's adjacency list, and we will be referencing by value. And after that we have visited, so vector int and visited. Then we have components, so vector int and let's just say comp and int id. Fine. Now what we will be doing here is we can take any method, bfs or dfs. Let's take bfs because I find it easy to do. So both are the same things, we can take any of it. If you are comfortable with dfs, you can do it dfs also. So q will be taking, and we will be inserting an AND operator between any two results. So yeah, so we will push the starting node into this queue. Okay, and visited of that starting node will be one that it's visited now. Fine. Okay, so while the queue is empty, we will traverse this whole component, whatever is connected to this node. F is q dot front, q dot pop, and this node will have a id which is comp of this node, that is starting will be equal to id, and all the connected connected nodes to this, means all the elements of this particular component will have the same id. Now this is, through this we did one thing, that we have identified that if the elements are belonging to the same component or not. If they are, then they will have the same value of the comp at their index, right? After that, what we'll be doing is that we will be traversing the neighbors of it. So for auto, there will be two things here. First is the next node to it, and second is the weight of the adjacency of this starting. Find. Okay, and and we will have to find an answer for it also. So let's initialize the answer, and now see how will we initialize the answer, as it is a AND. So while doing AND of anything with anything, the value should decrease or become equal to the minimum of the two elements, right? A and B is equal to or less or equal to the minimum of A and B. Okay, so we have to take, we will take int max here. The purpose of taking int max here is that because whatever value is there, if we do the AND of it to int max, it will be the number itself, and after that we can do the AND of any value with it, we will get the answer. So answer AND is equal to the weight, right, with this neighbor. And then if the neighbor is visited, if that next neighbor is visited, then we will continue, and if it's not visited, we will visit it, and we will push it into the queue. Okay, just a second. Yeah, fine. Okay, answer and yeah, it will do the thing, I guess it will do the thing, and we can return the answer here. Yeah, okay. Yeah, through this we have found the answers for all the components. And every time we go to a next node, we will increment the ID. Means we will change the ID to a different number because it will be a different component. Because if we're initially we are visiting 0, okay, we are visiting 0, 0 is not already visited, so we'll go into it. And while solving this function, we will visit every node that is connected to 0. We will visit 1, we will visit 3, and we will visit 2. Right? So they will have the same ID, that is 0. After that, the 4 comes here. Now, the 4 is not visited. 1 will be visited, 2 will be visited, 3 will be visited, 4 will be coming. Is 4 visited? No, it's not, because it was not in the same component as 0. So the ID is already incremented. So the ID will be 4 of ID of 4 will be 1. So ID of 4 and 0, 1, 2, 3 are different. So we know that they belongs to different components, right? After that, the question becomes just simple. We have found everything. We have got everything, so we can just make a vector which will be returning, and we can go to each query, that is auto queue of this, what's the name, query. So okay, and if the component of q0 starting point is equal to the components of q1, means both s and t, starting and ending point of this query, are belonging to the same component, then the answer will be what? Res dot push back the answer for this component, means the cost of this component, cost of components q0 or q1, that will be the same thing, no worries. Perfect. Yeah, so perfect. Yeah, we got this. And after that, if they're not in the same component, then the rest dot push back -1, it will be pushing -1 into it, and that is all. I guess that should be, just wait a second, belong to the same component, then rest dot pushback will be what? The cost of this, whatever ID of this component is, right? Initially the ID was 0, so cost 0 was what we need here for the, if the component is first component, like the 0th component. Okay, the cost will be this. After that, the cost will be 4. So if we are going from 1 to 2, yeah, it's perfect. The answer will be perfect. I guess you know it, like you can understand by just looking at the code. If you don't understand the way of doing it, by what I'm saying, because this question was looking hard at first, we see, because it has a big statement, and the questions with large statement becomes complex. Yeah. Okay. Okay. Type ID cannot have a name. What does this mean? What does this mean? Okay, is the okay, and what happened here? Okay, sorry. It should be this, and it should be this also. Vector pair. Correct. Yeah. Fine. Let's see what gone wrong there. So it's returning -1 into it. So it means that our ID was not set properly. ID was not set properly. Fourth was the component. Okay, fine. There seems to be a issue. Let's try to print the component vector like for int I0 to I less than n I plus plus and cout components I handle. This way we will. Okay, fine. Let's see if 0 1 2 3 belongs to same components according to what we have done. It should be, but I guess they are not. So it's 0 0 1 2 3. 0 and 1 belonging to the same, but after that it did something which it should not do. While the queue should be empty, okay, int node means we are popping from the front. Okay, component of f should be the ID. Okay, yeah, component of f should be. Sorry, yeah, it will be good now, I guess. Yes. So if we run this now, again, it's giving -1. So let's see what the problem is. Okay, we should be looking for the adjacency of this f, not start, right? And if we look into the answer now, it should be perfectly fine, I guess. Perfect. You can see 0 1 2 3 will have the same component ID, means they belong to the same component, and this will have a different component ID, means this is a different component. And also we can print out the cost dot size and cost I. So this will give us the whole idea of it, that whatever node have a ID 0, cost I, cost dot size, cost dot size, and we are returning cost. This will have a cost of 1, and this will have a cost of int max, obviously int max, but we have pushed -1 in place of it. We are not pushing this cost here. Okay, so that's why it's clear that for all those four, if any combination comes 0 to 1, 1 to 2, 3 to 0, any combination come, the answer will be what? 1, and rest the answer will be this. But if the answer if they're not belonging to the same component, then we will just push -1. So this is useless for us, doesn't matter. So we have got our answer. We can now try submitting it. And yeah, it's perfect. So see, the key is for this question is, it looks hard at the first glance. I also found it like a bit, but we need to break down this question into pieces. We need to see the concept. Like, first concept is the components. If there are two and the query has two vertices nodes which are not in the same component, they will have an answer of -1. So first thing we need to do is we need to identify that if the vertex belongs to the same component. For that, we need to set an identification for each node, that which component it belongs to. And we will set an identification for each component. Like, this first component has identification of 0 and second component has identification of 1. So whichever vertexes nodes have a same component, that will have an answer. Now for that answer, we will do the second thing. What's the second thing is that for every component, we have only single answer if we are talking about minimum, because AND operation is something, if we do as many values in the AND series, the answer will be decreasing every time. Okay, 7 and 7 will be 7, 1 and 1 will be 1. So it doesn't matter how many times we cross the same path, because it won't have any effect on the answer. That's why it's also given that we can walk over the same edge any number of times, because that won't affect our answer, because the AND operation will nullify it. Okay, so it's simple as that. This was the second concept, and now it looks so simple that for each component we need to find the cost. We can use DFS or BFS for it, because we need to traverse that particular component. While traversing it, we will set the identification the same ID for all the nodes in the same component. So that's the question. Yeah, like uh, maybe I was not able to explain this question as good, but I don't think I can explain this any better, because that's a complex question. If you try to do it, then only you will understand it. But it's a really conceptual question, easy question. You need to break it down into points, so that, see, at the last stage, what the question was. The question was just consisting of two things, right? Identifying if the nodes are in the same component, and the answer for each component is same. That was just the question. But initially it was a big question. It seemed like there were a lot of things involved in it, but it was just two things we need to do, and that's all. Yeah, so that's it for today. It was a really good question, half an hour to do this, but it was worth it. Really nice question, and that will be it for today.